Okay, good morning everybody. I'm Peter Thomas from Control Specialists. I'm going to give you a presentation on EMC for industrial communication networks. The idea of trying to install your networks so that we don't get any kind of electrical interference. Last night over a beer, Chris was giving me advice on how to keep this presentation short, and he said basically tell them to use an earth clip and keep the cable separate. So that's the advice, and thank you very much. Unfortunately, it's not always that simple. The reality is that I would consider all the mitigation techniques to be an insurance policy. Most of the time, you're probably going to get away with it. But when it goes wrong big style. And at that time, the solution is very often very expensive, very unpalatable. So what I'm going to do first of all is, I've done this for several years now, and as I mentioned before, I give the training on Profibus and Profinet, but when I'm not doing that, I'm on site fixing the problems. And one of the things that I'm seeing is the fact that we're getting more and more drives being used, and occasionally there are some significant issues on the networks caused by them, and it's not the drives themselves. And if I wanted to summarize it, it's simply that the drives are not being installed in line with the manufacturer's guidelines. It's as simple as that. And many times I've gone down with the respective installation guidelines and gone round and said, you've not done that, you've not done this, you've not done this. And they'll be saying, well, we've always done it like that. And therein lies the issue, that many times you get away with it. It's a problem that's going to get worse though, as I'll explain later on. So let me, because I saw so much of this, I thought I'd have a look into why are young guys coming out of apprenticeships, why are they not aware of this, why is this common practice still going on? So bear with me for a little bit. There's a little bit of background as far as the what we should be doing, and then I'm going to go into what the specific issues are. This is clearly not a reason that we shouldn't use drives. Drives are perfectly fine as long as they're installed correctly. And the likes of Siemens, ABB, all the drive manufacturers, they know all about this, but nobody bothers to read the manuals with any great depth. So let's have a look. I've aimed it basically for anybody that's responsible for the design or installation of fixed installations, and we'll talk about what that means shortly. But any basic installation comprising of high power switching devices such as VFDs, variable frequency drives, where we've also got a number of high speed networks, maybe Profibus, Profinet, could be Ethernet IP, doesn't really matter. It's also aimed at anybody that works in this industry that will have an awareness of the electrical wiring regulations. Not an in-depth knowledge of it, but clearly anybody involved in doing electrical installation will know about this. And what does that say about it? And then finally, for those people responsible for the auditing or fault finding on Profibus and Profinet networks. So just let's make sure that we're all clear on what EMC actually is. And it's a term that has two aspects to it, a source and a victim. So the source is any item of electrical or electronic equipment that will basically have the ability of generating electromagnetic interference. So from EMC point of view, it's basically limiting the amount of EMI that it can give out. As far as the victim, then it's got to be designed to operate in its normal environment. So by definition, there's going to be a clear difference between electronic equipment working in an office, working in a home, compared to working in an industrial process. As far as potential sources, then we've got all of these kind of things. And the ones in particular that I'm going to concentrate on, simply because I come across more of these than anything else, are the drives and the inverters in that list. As far as the victims are concerned, then basically this, signal transmission cables. So instrumentation, network cables, the sensors themselves, equipment, PLCs, and again, I'm really going to be concentrating on the first one of this because that's what I spend most of my time doing. There's a number of ways that this interference can get from a source to its victim, and not all of them are applicable to the world that we work in. There's going to be conduction. In other words, the coupling happens via the wires, maybe via the bonding infrastructure between the source and the victim. There is what's called near-field coupling, which is basically coupling within a few meters, either by inductive, which is usually caused by very fast changing currents, or via capacitive, which is caused by very fast changing voltages. Now, if you consider yourself to be a 50-60 hertz person, then by definition, if you've got voltage and current, they're both changing at the same speed, so you must have both. But as I'm going to explain shortly, in drives, it's slightly different, and we're going to emphasize one of those two as being a potential issue. What we're not normally concerned about is long-range radiation, the kind of thing that you would get in a transmission system. But that said, over the years when I've been looking into this, I've been talking to some very knowledgeable people in the world of EMC, and they came up with a term to do with what they call accidental antennas, which didn't mean anything to me at the time, but it brought it home as I started getting more and more involved. So we shouldn't completely remove the last one. So this was a very brief and useful slide given by a guy that came over to one of the PI conferences from Ghent University. And based on their analysis in industrial automation, in terms of sources, 90% of the EMC issues are caused by power electronics, switching devices, 10% other aspects. In terms of the victim, basically 90% of the problems are caused by bad grounding or reference. Now, I'm going to take issue with that word grounding, as we're going to see shortly. But fundamentally, these are the biggest issues that they're seeing, and certainly I can vouch for that in terms of my experience. So, if it's not obvious, what are these two terms? What we've got here are two conductors. The red one, a power cable. It might be a single conductor in a three-phase installation, could be 240 volts, just some kind of interference source. And in its vicinity, we've got a blue cable, which could be any kind of signal cable. It could be Profibus, Profinet, it could be a thermocouple. It's a sensitive bit of kit. This, at the moment, what you've got to imagine is that red conductor is live, but there's no current flowing through it. We've just basically powered the supply, but there's no current. What we've done there is we've created a capacitor, two metallic conductors separated by some insulation. So if we was to put a scope on each of those conductors, in the first instance, we're going to see a sine wave of 415 volts RMS. But we're also going to see a sine wave on the blue conductor as well, because we get what's called capacitive coupling. An electric field is generated around this or between these two conductors. So in a way that you would have two magnetic poles and you know that you put them together and they move apart, but you can't see what's going on. Well, here it's similar, except it's an electrical aspect. And we've got a bit of a problem because we can see a sine wave on our sensitive signal. Now, the amplitude of our sensitive signals is quite small, so we don't want this to happen. So one of the obvious things that we want to do is, as Chris told me last night, is to keep these two apart. So there's one rule. We'll assume that for now, because we're going to weaken it. The problem is that in an industrial environment, it is impossible to get that to zero, because as you move away from one source, you're going to come into contact with another source. So we've got to be a bit pragmatic and say, yes, we want you to run them separate from one another, but we're going to need a bit more help. If we now have exactly the same installation, but we now close the contactor to allow current to flow, then if we've got a changing current, we're going to get a change in magnetic field around that particular conductor. And if you've got some circuitry within the confines of that magnetic field, you're going to get coupling again, although this time driven by the magnetic field. And again, the basic solution is keep them apart. Okay. Now, I'm going to talk a little bit about CE. I've only literally just added the UKCA just to find out where we stood on that. So most of this presentation is based on the CE aspect, or the initial part of it is based on the CE compliance. But we've got to remember now that from 2023, January, everything sold in the UK that has to have a UKCA mark on there. From my understanding is that at the moment, technically, they are the same. So it should, in principle, be an administration process for an organisation with CE compliance to get UKCA. I'm hoping that I am correct in saying that.
Yeah.
Okay, so let's have a look at this Emc Directive. And the whole idea of this is, what are we supposed to do? That is the bottom line. What are we supposed to do? And this Emc Directive, one of several directives that's mandatory for a manufacturer of an item of electrical or electronic apparatus to fit the CE mark. And a lot of people assume that if they've got a CE compliant device, then by definition, they're not going to get emissions. And if they then make a system, maybe a panel, comprised of CE compliant devices, by definition, it must be CE compliant. And that is not the case. Now, what you get with CE is it is basically a statement that we are limiting the amount of emissions and defining the immunity of a particular device. The problem is that the world that probably most people work in here is not with a particular device, it's in an installation. And the technical definition of that is a fixed installation. It's defined as a particular combination of several types of apparatus and, where applicable, other devices which, for example, electrical or electronic components forming part of an electrical or electronic circuit. Thyristors, transistors, etc. They're going to be in a fixed location. And it's not possible to get CE compliance for a fixed installation, because it's so dependent on its location, the installation techniques that have been followed, etc., etc. So arguably, there is a possibility that you might have the best equipment in the world, but it's the installation techniques that have actually let you down. So the use of several EMC compliant devices in a fixed installation will only result in an EMC compliant installation if the system as a whole has been designed and installed by proven EMC techniques. Now, one of the things I gave a similar presentation several years ago to PI in Germany, and I was introduced and they said, Peter's got something new to tell you about EMC. And the first thing I said was that one of the standards that I'm going to point you to has got a date of 1997. So, don't shoot the messenger here. This has been a message that's been going around for a long, long time, but nobody's aware of it, or very few are aware of it. So, basically, how could we do, what's the procedure then of achieving EMC in a fixed installation? Well, okay, first of all, only use equipment that's known to comply the standards, use CE compliant. Ensuring that the equipment is always installed in line with manufacturers' EMC guidelines. And therein lies the issue, because very, very rarely, from my experience, they get away with it, but sometimes they don't. Risk assessing the installation from an EMC point of view. We're going to briefly talk about the grounding of shields and what we would recommend from an EMC point of view, and then what the hazardous area standards say about doing exactly the same thing, and there's a bit of a conflict there. Ensuring that electrical designers and installers are aware of the techniques of ensuring EMC compliance in a fixed installation and following them. My general view is, if you consider yourself from a 50-60 hertz background, and I'm one of those people, a lot of this stuff is not on your radar. And the young guys coming out of their apprenticeships seem to have been taught by the same guy that taught me in my apprentice, because the story's not changed, basically. And therein lies the issue. Controlling change during the life cycle of the system to ensure that EMC compliance is not compromised. So it could be that you're getting away with it at the moment, and then you come along and put a new drive in, and that tips you over the edge, and all of a sudden you've got a problem that you didn't have before, which I'll explain again. What I decided to do when I was looking into all of this, I thought, why is this happening so many times? So It's a long time since I had to do anything to do with the IET regs, but I bought myself a copy and I thought, well, I'll have a look at what it says about EMC. And there is a section in there, but it's only 4 sides of A4 paper, 4 or 5 sides of A4 paper. And it primarily deals with these topics. Low voltage distribution systems. It does mention earthing and equipotential bonding systems and cable segregation, so that's quite good. Doesn't mention anything about shielding or anything like that, so I'm thinking, well, no wonder this is happening then. It does, though, identify specific sources of EMI interference, so variable speed drive, so there's a little bit of a link to the world that we work in. But there's a bit of a get-out clause, and you've got to remember that this document, or documents like it, are going to be read by installers from a wide range of industries. Some of these people will be fitting bathrooms and kitchens. They are not really interested in EMC in the world that they work in. But conversely, it could be people working in the installation of large industrial complexes. So what does he have to say about it? Well, he has a section in here, and it's effectively what's called a normative reference. And what a normative reference is, it's a reference to one or more documents that are implicit in conforming to the main document. In other words, or in my words, if you work in the world where EMC is likely to be an issue, you can't claim conformance to this standard unless you also claim conformance to the following. And we have these. BS 6701, telecommunications equipment and cabling. 50310, telecommunications bonding. Information technology and cable installation, and then the real killer, 61005-2, 1997. So people from anybody that's been doing electrical installation over the past 20 odd years, even if they're not reading that particular standard directly, should be reading something very similar to it. And this is what is classed as following good engineering practice. And by definition, if you don't follow that, well, you're not following that good engineering practice. Okay, so there's the background. Yes, if you read deep enough, the guidelines are there. We should be doing it, but being realistic, most of the time, most people don't do it, and most of the time they get away with it. But there's lots of things that are going to change. Let's have a look at a variable frequency drive then, in a block diagram format. It doesn't matter whose it is, but it's made up of 3 particular sections. There's a rectifier section to convert the incoming AC into DC. There is the DC bus section, which smooths it to give us a constant voltage in the order of about 600 volts. And then there is the inverter section, which consists of high power switching transistors. On the left, we're going to feed it with an AC 415 volts AC supply. So no big deal here. But from my experience, there are many people that basically just think this is a magic box of tricks and that it's 3-phase in and it's 3-phase out, but it's a variable frequency. And if I ask them, well, what would you see if you put a scope between the red and yellow phases? Almost always they say we're going to see basically a sine wave. So, okay, nothing new there. I then ask, well, what would you see if you put it between the red and yellow phase on the motor? And they say, oh, a synthesized AC waveform, a noisy waveform, etc. Well, no, you don't see that at all, because these transistors can only be on or they're off. So what we're going to see is what's called pulse width modulation. So a year or so ago, I happened to be working with a guy that had an induction motor controlled by a drive, and I thought, well, this is a good opportunity to put a scope on. So basically, what I did was set the speed to a certain speed, and I'll have a look at the waveforms. And these are the waveforms that I saw. Well, before I go to that, I'm talking ahead of myself. This is what we see on the voltage. It's on or it's off. That's all it's doing. It's the width that's changing, and when you apply that to an induction motor, it will integrate that and it will draw a current that will approximate to a sine wave. So it's certainly a sine wave from a current point of view, but from a voltage point of view, it's significantly different. It's on or it's off. Now, here's the slides that I wanted to show you. Taken using an oscilloscope connected between two phases of an induction motor whose speed was being controlled by a variable frequency drive. Now, these look small, but I had quite a large scale on there, but you can see them. These are the pulses. On this one, a 1-200 range, so basically they are 600 volts. And you can see as we increase the speed, it's on more times than it's off. So that's all we see. Now, in this particular case then, we've got some voltage switching on and off a lot faster than the current. So the kind of interference that we're likely to get from the motor cable is more likely to be capacitive coupling, because capacitive coupling is dependent on very fast changing voltages. The switching, the on and off switching of this, is a parameter that you can adjust in the drive, one of the drive parameters. It's called the carrier frequency. And it varies between 4 and about 16 kilohertz. So 16 kilohertz, imagine switching an electrical contactor on and off 600 volts 16,000 times a second. Despite the fact that it might fall to bits after a very small time, you are instantly thinking of noise. It must be a noisy device, and by definition it is. But it gets even worse than that. So that's what we've got there going along. So VFDs by nature are noisy devices. Siemens, ABB, Danfoss, they know all about this, and they go into detail of how to limit the effect of this in its environment. So, the switch-based nature of the inverter section of a drive makes the cable between the inverter and the motor a significant emitter of EMI. This carrier frequency, which can be varied in that particular range, is the bit that's going to cause us a problem. And without special precautions, the emissions from this cable are going to be much higher, and in fact will be in the order of megahertz, not kilohertz. Now, I can quote all of these kilohertz, megahertz. We need to somehow relate this to some physical dimension here. What does it mean? Why are we as 50, 60 hertz people not really even bothered about this kind of stuff? So, when things get bad, these emissions can have an adverse effect on low-level communication networks. So here's a number of potential sources of disturbances and the approximate range that we might get. As we get higher in this range, the amplitude of the emissions do in fact get smaller, but nonetheless they are there and we need to be aware of it. And one of the things that I'll be talking about shortly is something called the frequency of concern. So whenever we've got EMC issues and we're trying to improve the system, we need to know, well, what is the frequency of concern, because that's going to tell us basically how much we've got to spend on this to improve things. So basically, the mitigation against the emissions from this pulse width modulation are generally associated with adequate cable segregation between the cable and any sensitive cable. So the PI, we're basically saying at least 20 centimeters. A low impedance bonding of the drive, motor cable, and the motor and cable shields, where impedance is low at the frequency of concern. So when most 50, 60 hertz people see the word bonding, they're generally thinking of green and yellow wire. But whenever you see green and yellow wire, that is safety bonding. So I'm not here to tell you anything new about electrical safety, but what I will say is, if you've got a bonding infrastructure that is full of green and yellow wire everywhere, it will be completely safe, it will meet the electrical safety standards, it will not give you an EMC compliant bonding infrastructure. You might get away with it, but they're the kind of things that we need to improve. So one of the standards has long since said that star earthing, where you might have two distinct panels with an earth bar, where two long cables going to a main earth terminal, it's long been said that is good for electrical safety and bad for EMC at all frequencies. So it's in the document for you. All of these and more will be detailed in the installation guidelines of the guidelines, with low impedance bonding and all of the consequences of that being detailed in this 61005-2 1997. Okay, so what about the cable then? What can we use with the cable? Well, it seems to vary. Some people just put three-phase cable with some armouring because it was three-phase in, it's three-phase out. Some people do that. Some people have a cable with an internal PE. Some people decide to take the PE outside, the PE being the protective earth, they take it outside of the cable. But what the recommendations are now is that you're going to get more likely of an EMC compliant installation with symmetrical motor cable. Now, Paul from Belcom is in there somewhere, and he was telling me they're getting more and more inquiries for this cable. It seems that the message about EMC issues is getting around. The problem is, we've got to be very careful about how we demonstrate good engineering practice, and one of those is to follow the installation guidelines, as I've said many times. And you will find that different drive manufacturers recommend different things. So for example, one manufacturer will say, this is what you want. We want a shield. You can have an armour on there for mechanical protection, but we want a shield. Another reputable one says an armoured cable will be fine. So what do? We need to follow the guidelines, but I know for certain when I've discussed that with EMC consultants, they've raised their eyebrows as to whether that is actually going to be good enough. But this is where industry is starting to move towards, but by definition, it's an expensive cable, so it's not particularly popular. This is the cable that it looks like. I'm going to explain the benefits of that shortly. Okay, so the world of EMC, the strange world of EMC. The earthing, the grounding of shields. If you say earthing or grounding in the earshot of an EMC consultant, he will shoot you, because it's an immediate indication that you don't fully understand what you're talking about. And I was the first person to be using the word grounding and shielding, and I still do, because it's built into you. But it's quite a topical picture here, an aircraft. If you got one of these aircraft, you would hope it was EMC compliant, and depending on which school you come from, the grounding the shield at one end, the grounding the shield at both ends, well, in that respect, then the only way you're going to be able to achieve that is to do this, which doesn't make any sense whatsoever. So basically, what we do with the shield is very important, absolutely certain. But the terminology is, we should terminate the shield, and this is, I know this for some of you will be contentious, we terminate the shield at both ends to a common reference. Now you might think I'm just saying it for the sake of it, but a common reference means a piece of metalwork that there is no, in theory, no potential difference between the two ends. That's what a common reference is. But let's move further. Earthing and grounding and EMC are completely separate issues. We talk about earthing or grounding cable shields, but the important aspect from an EMC point of view is that the shields are connected to a common low impedance reference. Now, you guys will be thinking, well, we connect it to our bonding infrastructure, so we're doing that. Well, this is the problem. The fact that this common reference is usually connected to Earth is a safety-related matter and nothing whatsoever to do with EMC. In other words, you can, as long as the two bits of metal at either end are at the same potential, and you ground the shield, and there's a common, it does not need to be Earth from an EMC point of view. So I know this is being recorded, so I am not recommending anybody have a solid piece of metal without bonding it. That's a safety thing, a different matter. We have to accept, though, that it is common practice. Grounding and earthing just still gets used. Right, this is the reality then. One end or both. Well, I was from the school of one end, and the vast majority of people, even nowadays, still seem to be the one end. Now, it doesn't mean that they were wrong. What it means is a lot of the electrical circuits have changed now that it's no longer applicable. And what is for sure is that the only way a shield can protect you against both electrostatic and electromagnetic coupling is for the shield to be bonded to a common reference at both ends. And that term applies to most modern day balanced transmission systems. What we mean by a balanced transmission system is that every conductor in the cable has got some signal on it. You are not going to be grounding any of those internal conductors. Now, single-ended shielding, in other words, grounding, earthing at one end, still has its place, but it's primarily to unbalance, where one wire is a 0 volts or a ground that you will literally connect to ground, and then there is a signal relative to that. That's still applicable, because if we do it bonding at both ends with this, we get an earth loop. Unfortunately, it's a practice followed by many installers. So, this is basically what we've got here then, that we've got some kind of source. There is a magnetic field around it. We've got our particular shielded cable, and if we connect our shield at both ends to this common reference, basically a current will be induced in that shield, and basically it creates an opposing magnetic field which gives us the shielding effect. That's what we would like to do. So by definition, if you only ground at one end, then you have no protection against magnetic coupling. But if you haven't got a source of magnetic coupling, it's not a problem anyway. Now, safety is clearly paramount here, and the problem is that the bonding infrastructure that we have, whilst it might be electrically safe, it's far from ideal when we come to electromagnetic interference. And it's actually possible for two distinct grounds around a large installation to be up to 50 volts difference. It's called a touch voltage, and that's long been the case. That's not a common reference. Common reference is very less than a volt, millivolts. So what we're saying is, if you've got two panels, large distance between them, and you're running Profibus or Profinet cable, and you follow the recommendation of grounding the shield at both ends, there is a possibility that you might be putting 50 volts across that shield. So now our shield becomes an equipotential bonding conductor, which it wasn't designed to be. So when we say ground at both ends, there's a kind of an unspoken statement on the assumption that this is a bonding infrastructure designed for EMC as well as safety, which not all of them are. Several IT and telecommunication standards say that it needs to be less than 1 volt, and others saying, well, it can be whatever it is, as long as it's that at the frequency of concern. And the frequency of concern is what frequency is causing you a problem. So in the drives, for example, well, drives give off a few megahertz, so okay, the frequency of concern for drives is maybe a few megahertz, and that's how we would go along improving things. So, bonding and the skin effect then, this is something else. We've got a normal green and yellow conductor there, and often used for bonding bits of metalwork together to form our bonding infrastructure. And there is absolutely nothing wrong with that for 50-60 hertz safety. The problem is that all of the cables for a 50-60 hertz installation are all sized for the currents at 50-60 hertz. And I've got nothing new to say about that. And when you are sizing it, you are assuming you have got the full cross-sectional area of the copper to play with. It's just a given that the current flows in all aspects. But we're now living in a world where we've got higher frequency currents, possibly in the order of megahertz. Now it's a different world. When we put the same amplitude of current, or try to put the same amplitude of current through a conductor, it will flow on the surface. It's literally not possible for the electrons that make up the current to flow in the middle. So basically, whenever the current comes to something like a green and yellow wire, it's going to be a relatively high impedance, and he's going to try and take an alternative route back to his source, which he often does. So this is why, for bonding, braided straps are recommended, because they've got a bigger surface area. So these are going to be good for electrical safety, and they're good for EMC as well. And generally, if I go round on sites and I'm opening a panel door and I see a green and yellow earth wire, that doesn't immediately mean to me you've got problems. It just means to me that whoever's designed this have clearly not had EMC on their mind when they've been designing it. So that's where we are there. So the increasing use of high-frequency switching devices can result in bonding cables carrying currents at frequencies much higher than 50 hertz. So you've now got to think now that your bonding infrastructure, which is electrically safe, might not be a low impedance to these high frequency currents, and if it's not, they're going to go by whatever route they can back to their source. We will have uncontrolled flow of these currents. The impedance of these cables at higher frequencies can result in currents flowing back to the earth via a lower impedance route, but that are not necessarily designed for doing that. This is one of the standards, 61005-2, and what it's basically saying is that they would like a brand new installation to move towards this idea, a mesh bonded network, where you've got lots of metalwork in between, such that by definition it's impossible for potentials to exist between them. The dimensions of those meshes depends on the frequency of concern. So if we're at very, very, very high frequencies, it's going to be small, but maybe more like meter size for the lower frequencies in megahertz, etc. Now, this was the bit that brought it home to me. EMC consultants have this term accidental antenna. And they basically, when they're in an environment of industrial automation, they basically say any metallic structure whose length is a sixth or more of the wavelength of the frequency of concern is considered an accidental antenna. In other words, it has the potential of radiating beyond its confines. Now, 3 megahertz sine wave, 100 meters is the wavelength. A sixth of it is 16 meters. So potentially, if you've got any metalwork in the order of 16, 20 meters long, there is a potential for it to resonate when we've got emissions at this, no matter how small they are. I'm not saying it's going to happen, but this is the world that they live in. They're looking at this kind of thing.
Does your earth bonding account for that?
Yeah.
Add that 16 meters on?
Yeah, it's metalwork. Yeah. It's a length of cable tray, vertical struts. It's potentially, so it could emit around the building. So, and yeah, I just worked that out based on, in a vacuum with copper, it's going to be slightly less than that. So, conventional equipotential bonding cable is a form of what's called parallel earth conductor. And this is all described in these standards. And basically the use of wire, green or yellow wire, 50, 60 hertz is fine. But basically, they look at alternative PECs. So nobody's going to start digging new holes in the ground to improve EMC. Nobody's going to do a site-wide bonding infrastructure. They will look at how can we lower the potential between these two. And this 20-odd-year-old document tells you exactly how to do it. It could be the cable trays, the structural metalwork, and low impedance bonding between straps. So, have I got 4 minutes now? I'm now going to increase my speed and show you what happens when it really goes wrong then. Bad practice from an EMC point of view doesn't necessarily mean that you're going to get EMC issues. Most people get away with it. When there are, the problem is what you're telling these people they don't want to hear, because it's generally going to cost them a lot of money, either in lost production or in the cabling and the rerunning of it to sort the problem out. I've taken several slides over the years at various places, all installed in quotes by competent 50, 60 hertz electrical people. So here's the first one that I did many years ago. I was in a room probably about this size, down the centre, lots of Profibus hubs, etc., plugging in an analyzer, and the analyzer was telling me the network was perfect. And then all of a sudden it just died. No obvious reason, but I was just aware that all around me were wall-mounted drives. So we got permission to take the front cover off one of the drives, and we only chose it because it was a big one and it was very near a main socket to allow us to plug some equipment in. Here's the drive. Here's your three-phase cable here. So you can see 3-phase and a PE in that cable. Here is your motor cable, the 3-phase and a shield, and there's a couple of Profibus. We took this guy here. This is basically a 4-channel clip-on ammeter. So you can see I've got the clamps on each guy. They are no different than the clip-on ammeter, with the exception that they've got a higher frequency range. So and instead of displaying the current on an LCD screen, they display it on a web server. So we clamped this on, we stood well back, and then we said, switch it on and let it do what it's normally going to do. And the question that I ask everybody, what would you expect to see on that clamp there, the red clamp that's clipped over the green and yellow protective earth, the earth wire, whatever you want? And most say 0. Some might say a few milliamps, something like that. Well, what you're going to see now is typical of a drive that hasn't been installed in line with the manufacturer's guidelines. And I've seen this many, many times. Look at the top. Amps, 12 amps in that PE. Now, the guy that I was with at the time invites people to come along and touch the earth bar. And nobody's actually gone along and touched the earth bar because they're now living in the 50, 60 hertz world. This shouldn't be happening. How is this going on? Now, I can tell you lots and lots of stories about this now, but we haven't. If it's interest, come and see me and I'll talk to you about it. But this is now, that current is not flowing out of the drive. What is happening, you've got capacitive coupling from the motor cable getting into the bonding infrastructure because these guys have twisted the shield. That's a high impedance. It's gone into the bonding infrastructure and now it's coming back into here. Now, that is megahertz, not 50 hertz. Think of your accidental antennas. There's all sorts of reasons, and it's took them years to gradually improve these kind of things. Look at this guy here. This was only a few weeks ago. This is a drive where you've got a little simmer code at the bottom with Profibus cable in and out, and they can't operate this network unless they unplug the Profibus cable. They had to operate the drive in manual. They took, as long as the cable was not plugged into that simmer code, the network worked fine. This is what I saw on the Profitrace. Now, for those of you that know about Profibus, then Profibus uses what's called RS485. It's a 2-conductor transmission system. This isn't the signal on the red or the green, it's the difference between the two. So clearly there you think, ooh, okay, that doesn't look right. We're normally looking for nice square waves. But this tool has got a useful feature where it allows you to look at the signals on both. And you can look at the signals on the A and the B. And when you do that, it's always a good way of saying this is EMC. Look what we see on the individual ones. And the telltale sign here, if you can just see on the right, it just returns to normal ons and offs. And with RS485, if it goes up on one line, it goes down on the other. There's a mirror image. Whereas here, they're clearly in phase. And that's 100% certainty. This is EMC. Now, we knew it was this drive, but then we could start to have a look. Those black cables going up, they're the 3 individual conductors for the motor. You've now got capacitive coupling all over the place. So what we did, we took it a little bit further, and what I did was I took the cable off. So this guy now is completely removed. I plugged him into the Profitrace. I just set him up as for those of you who know that what Profi Captain is and a Class 1 Master. I just got him to talk to that guy and we got them to manually start the drive, and that's what I saw. So it's coming through the simmer code onto the network, primarily because of all this poor cable segregation, and then multiply that by about 10 of them because they've got them all over the place. And then a couple of others on here. You can see there, this was a warehousing. They called me in the pandemic, basically saying they weren't very happy with the installation. They wouldn't let me on site, so I sent them some gear down. They improved it. Went down, problems. They've said they had only grounded at one end, but they asked me when I went down, would I check another one that they hadn't yet done? And that's the one that they hadn't done. And you can see sine wave. You don't expect to see a sine wave on a Profibus network, and it's in phase. So basically, that is it. The tools that we need really are things like this: a spectrum analyzer. Most will be aware of a scope, where the x-axis is in time. This is a spectrum analyzer where the x-axis is in frequency. So we can basically see and go around with probes to say, well, there's the emissions from the drives, and you can try to correlate those emissions around the plant to say, well, he's obviously causing this. What do we need to do about it? Right, I'll slow down now. For more information then, there's those two documents. 61005-2, or the 2 of note. If you're interested in more, we did put a training course together which we called EMC Awareness, where we start to show you some of these things, and we get a spectrum analyzer out and stuff like that. And then, as I mentioned earlier, we are accredited to the Certified Profibus, Certified Profinet. We're doing an industrial Ethernet one now, and completely sidebook PID loop optimization. If you're interested in PID loop tuning, that's what I used to spend most of my time of years ago, either designing control systems or doing the tuning. So that's something that some people are interested in. But there's my details. If it's of interest to you, give me a shout. There we go.
Thanks, Peter.
Okay.